I want to do a quick video with some extra details for your project. One sort of caveat, one warning. Um, so one student was prototyping with the new op amps, and one thing about the quad pack op amps is they're actually capable of sourcing a huge amount of current, more than some of the others. They're also faster than some of the other op amps, and there's a possibility that it creates an instability. We were seeing some weird behavior in the lab, and so I just want to kind of warn people about that. So one issue, if you look at this circuit, this op amp circuit, the idea here was we're driving current through this battery to maintain this voltage here that equals this voltage here, and and the assumption is the op amp outputs whatever is necessary to keep this voltage the same. However, sometimes with op amp circuits, especially when you have comparators and resistive pathways, there can be sort of spurious, momentary glitches that happen. So for instance, somebody's hand touches a circuit board, somebody's hand touches this voltage divider, tiny little spark discharge, or maybe there's just, the charges on the surface of their body or something, right? Some momentary change in this voltage here. And especially if it's a quick momentary change in voltage, the op amp will try to react to that. And sometimes, in some cases, the op amp will react to those momentary changes in a way that that causes it to perform outside of its range of operations. And in this case, if for any reason there's any little squirrel or squiggle or wrinkle that causes this op amp to have its output drop low. So if this output for any reason when it's trying to operate normally rails low due to some momentary change in some signal somewhere, what's going to happen is if this drives low to 0 volts, the battery is going to act as a negative power supply, and it's going to drive this pin. It's going to drive current. It's going to drive this low. So you're actually going to start to have current flow the opposite direction through this resistor. So you're actually going to get a negative voltage at this terminal. And if the voltage at this terminal, according to the datasheet, if the voltage at this terminal ever momentarily drops under 200 millivolts below the bottom rail, that will cause this to be unstable. So, there's several things that can cause this. Anytime you have these sort of resistive dividers, these resistor dividers here that are highly resistive, the nice thing about them being resistive is they don't waste a lot of power. You don't have a lot of current just burning through these. The downside about them being highly resistive is high impedance signals are more prone to noise. So especially when you have things on a breadboard, you have giant loops with wires. And if you have something switching, which especially students who are doing the oscillator circuit, or even students who are doing, switch on an LED, switch off an LED, you have potentially fairly large transients of current. So you might have a wire going to an LED that, all of a sudden it'll go from 0 to 5 milliamps. And if that happens, that's going to produce a flux, and that's going to interfere with any other place you have a loop. It's going to induce a current in that loop. And if that loop is a very resistive loop pathway, even a tiny little current is going to produce a voltage. And so it can cause these sorts of errors. And there's a few things that people do to fix this. So the normal way to sort of avoid these like little momentary transients is to do what's often called decoupling. Decoupling is a way of using capacitance in order to prevent rapid changes in current from affecting a voltage. So for instance, if we're powering this op amp with 5 volts in ground, quite often we would add a decoupling capacitor. So we might take a capacitor. Let's just do the manufacturer part. I almost guarantee you I'm not signed. It says I'm using it, but let's see. We do. Okay, yeah, so this looks good. Here, let's see the footprint. Oh, we can always change it later. No, we can't place. Well, it's going to do this to me again, isn't it? So weird how it does it. Oh, it'll show me the part. Verify 0603. Go for the one with the biggest pads. Yep. Place. Okay, so commonly what we would do is we would take a capacitor like this. We would connect one side to ground and the other side to IB0. Okay. And then this capacitor is basically, it provides, we can think of a capacitor as sort of a storage of charge. It provides this when there's a momentary change in current, rather than having that immediate change in current result in this resistive drop in voltage and generate this flux. Well, it'll still generate flux. But this capacitor sort of gives it allows a momentary surge of current to flow without changing the voltage on the rails. So normally if we have any, especially with digital devices, things that switch rapidly, we normally would always decouple them because we don't want these momentary surges in current to affect the voltage. Sometimes when that happens, if the voltage drops, it can create an effect internally, an undesired effect, which causes an instability. Another thing we do often is we put a small capacitance in parallel with the resistor that's generating this reference voltage. So this resistor that's generating a reference voltage here, it would be pretty common to, well, I'm going to mess up my schematic if I do this, but it'd be pretty common to do something like this, to put a capacitor in parallel like this. And that's going to, again, if there's a little squirrel on this voltage rail, if there's a little wiggle on the voltage rail, this capacitor is going to hold this same voltage relative to ground. Another issue that's much harder to get rid of that causes these sorts of instabilities is current on the ground loop. So when we put ground symbols here, when we build our circuit, we're kind of assuming, right? Oh, this is all one giant sheet of metal. The assumption throughout your entire time, for the most part, in electronics is anything that's connected by a piece of metal all has the same voltage. That's not actually true. The metal has some resistance to it. And so when you have current flowing through this metal, even if it's a ground plane, even if it's a metal plane, when you have current flowing through it, you're going to have some voltage drop. So every device is going to have a slightly different ground. But more importantly, if a device downstream of it starts to draw more current, as that current flows through the ground path back to where it's coming from, back to the USB connector, there's going to be a drop along that ground path. So if I'm a device and I'm sitting here with 5 volts in ground and somebody else over here is switching, it's possible that my ground is kind of doing this sort of thing. And there's not much you can do with those ground loop things except to minimize the ground resistance. That's very difficult to do in breadboarding. So I see a lot of your breadboards, there's, really your ground pathway is a really long string of jumper wires and rows and things like that. And there's a bunch of connections, right? It's a mechanical connection. It's not a solder joint or anything like that. So breadboards are especially bad about this. And you'll see it when we get to switching regulators. That's really when it becomes an issue, because switching regulators are operating in the hundreds of kilohertz. And so trying to implement them on a breadboard is nearly impossible. Actually, I don't try anymore with those fast ones. I used to do it, but almost every student who tried to breadboard one of these switching regulators would get some instability in the feedback path that would cause it to just lose its mind. So these are a couple things that can cause these sorts of issues. But in this case, this is a pretty critical thing where if for any moment anything causes one of these instabilities, it can have this sort of disastrous consequence. So it can have this, I'll probably just delete this. I might leave the other one, but So it can have this disastrous consequence. And one thing we can do to fix this is we can, so the issue here is if this goes down, if this voltage drops to 0, you now have a negative voltage at this node in ground, which means current's going to flow in this way. So the battery, rather than charging the battery is going to start discharging. And we want to avoid that. We want to avoid that from happening. And so to avoid that, one way to avoid that from happening is to put a diode here. We didn't want to put a diode originally because a diode is great here in terms of avoiding, the reverse, in terms of doing reverse polarity protection. It's not very good in terms of the voltage drop, because if a diode, even a fairly good Schottky diode, is going to have 0.3, 0.4 volts across it when it has current flowing through it, so it's going to get this drop. But I think for most of your designs, that's actually going to be fine if you end up putting a diode. I'd strongly recommend everybody do a diode, even if you don't end up putting the diode in there. Even if you realize, listen, my design works great, I don't need this diode, I don't need to protect it, I tested it, it's fine. Then you can just, instead of putting a diode, you can just put a wire, or you can just short the traces together or something like that. So I can show you how to do something like that in here. But if you don't want a diode and you don't want to have this ugly wire in there either, I'm going to show you how to do it. So first of all, let's have a diode. So let's put a diode here. So to do that, I'm going to first break this wire. And for me, I always like to update. I added this capacitor, so I'm gonna have to annotate it. But I always like to update after I cut a trace. I like to update to let the software know, hey, this thing's not connected anymore. So update PCB document. Yeah, and it's not happy here. So yeah, so now it's getting mad because now, these things, it's throwing these errors because these things are now disconnected and I have them connected. So it sees that as an error. So just to be able to see what's going on here, I'm going to go back to my top layer. And I'm going to hide this ground pore. So tools, polygon pores, shelve it. So shelving the polygon pore. This drives me nuts. Altium, as soon as you put bottom bottom silk screen, it just covers everything. It takes priority, and I don't know how to hide that. There's this kind of layer option. I don't know this view priority, how it... Anyway, you can hide a layer if it's driving you nuts, but it drives me nuts that it always shows up on top. Anyway, if one of you finds out how to do it, let me know. Option there. Wow, I don't know. Whatever. So yeah, it doesn't like that we have this here. Actually, that layer's driving me nuts. Okay, so yeah, so it says, hey, guess what? You're not actually connected here. And actually what it did is it changed the actual signal assignment on the traces too. So we're gonna have to redo these. We can change the trace. Oops. There's probably a little squirrel of copper here. A lot of little squirrels of copper here. Okay. Anyway, so we get rid of this copper. Yeah, so it changed the net name of this copper. That's why it's throwing this error. So, we should clean up that copper or change its net name. And then we can go back in and place a trace. Sorry. So we want to add now a diode here. There we can, usually a through hole is fairly safe, but modern diodes, modern Schottky diodes, Schottky diode is designed to have a very small forward voltage. So this is really what we want here. We want something that can carry 10 milliamps of current with very tiny forward voltage. And modern ones that use modern PN junctions that achieve really low forward voltages are often not available in through-hole packages. So it's unlikely you'll find the most recent technology in through-hole. So I want to show you one part that we have. So one part that we have available in the parts library, and it is right here, LSM 115JE3. You search for it, you can find it. And so I want to show the, let's look at the data sheet for this. Data sheet. So if we look at the curves for this, the forward voltage at current, so we're looking at we're operating this diode right around here, right? 10 milliamps of forward current. So this is going to have a forward voltage of almost nothing. I mean, it's going to have a forward voltage of 10 millivolts or so of using this. And again, this is you can't find this in a through-hole package. And actually, this diode is fairly expensive. So this is I think we bought a reel of these, and I think it cost 25 cents each. So this is about a $250 reel of these diodes. One thing to note is when you're using diodes, when you're relying on diodes, there's a huge temperature when you're operating in this current region, huge temperature difference. So at high temperatures, you get this improved performance. We're actually going to be operating closer to room temperature, which is going to still be under 100 millivolts, but it's going to be fine. And the reverse leakage is even worse. So the reverse leakage is usually pretty high as you get to higher temperatures. And what's happening is just the higher the temperature gets, the more these energy bands in this PN junction sort of start to blur. You get electrons kind of and holes sort of spilling over to each side. If you want a low voltage diode, you need to have a very small energy differential between your P and your N region. And the problem with doing that is you're always more sensitive to temperature. So just as a knowledge of using diodes, these modern diodes are great for their performance, but the problem is they're heavily temperature dependent. So for a lot of designs that, a lot of especially automotive designs where it has to operate between minus 40 degrees C and 160 degrees, or not 160, between minus 40 and I think 80 degrees C. I can't remember the full range of values for automotive, but it can be difficult to rely on the performance of these new ones for that. But for this application, consumer electronics, it's pretty good. You have a pretty good assumption that this is going to be operated, around 20 to 40 degrees C. So this is, at 25 degrees C, we're looking at the forward current at 3 volts is going to be under a milliamp. So this is going to be, so for our purposes in terms of blocking current, this is probably going to work just fine. It's not going to have this situation of there's reverse current flowing that produces this really big negative voltage that exceeds the spec requirement for our op amp. So if we're going to use this, which I think we should after looking at the data sheet and the fact that we have it, let's pick a footprint that's big as possible. So it looks like this IPC-A is the biggest one that we've got. And then let's place this. I'm sure I got logged out of Altium now. Oh, look at that. Good. So we're going to place this diode here. And we're going to rewire this. Okay. And now we're going to update our design. Or no, we're going to annotate it. And then update PCB. And it's probably going to throw a fit again because we have all this. The problem is we have all this metal, right? We had all these little metal traces, and all these metal traces were assigned to, they were all assigned to one thing or another. And they were assigned to one signal or another. And now that when we change those connections, we change the signal without deleting that metal layer. Sometimes the metal is in a weird spot. So Okay, so this thing needs to be. Um, okay, so let's just clarify. So this is the output. This output is going to need to run through this diode. Um, okay, output's going to have to run through the diode. And this is our out. Okay, so we can reconnect here. Oh, we can't because it's. Oh, I see what's happening. That's right. Feedback after that. Is that right? Feedback after the diode. You know, actually, we want to move this. So we still want to measure. We don't want to measure the voltage after the diode. We still want to measure the voltage out of the battery. So this test point needs to be moved. And it's going to be moved. I might throw a fit again. Okay, so now we have a slightly better, yeah. So now we've got to get the, we've got to get this pad over to here, and there's not really a great way to do that. And once again, okay, one thing I can do is we don't have to have this trace wrapped around like this. So we can, so all we have to do is get to there. So we can just run this. We can do that, and then we can put this diode kind of wherever we want. I'm going to put it at the top. We'll be carrying some current on this, so we'll be carrying up to 10 milliamps on here. So let's just do 8 mil or so. Bottom side. There's the current flow. Current flows through here into the battery. goes out of the negative side of the battery. Oh yeah, back into BT101. Okay. So this does, yeah. So this does carry a fair amount of current here. So I'm going to fatten this up. It's not going to make it easy on me. Can't go quite as fat with this now. That's fine. Okay. All right. So looking. Oh yeah, my decoupling cap. Now the thing is, whenever you have a decoupling cap, wait, why did that not get us? Oh, because I'm not showing this. That's right. Okay, I gotta go back to. If I want to see this, I gotta go back to all layers. Oops. Yeah. Okay. Yeah, I just did that to hide this stupid bottom silk screen that drives me nuts. Okay, so we do have this diode stuff. We have this annotation. I'm just gonna manually change these to. Now, it doesn't really matter where we put this diode. This is a decoupling diode, so it's just between power and ground. So it's really any convenient place where you can find it. And you don't have to populate. If you put a decoupling cap, you don't have to populate it. It's just going to, and although if you can put it anywhere, I'd recommend putting it somewhere near where your ICs are. That's usually the best place to keep it. Boy, I gotta tell you, this layer here is driving me nuts. Neat. See, it's a little risky to do that but it's annoying. There's probably an order thing. If somebody find that. If somebody finds this, somebody finds where that diode has that, how to change the layer so it's not so visible, let me know. I'm gonna hide it for now. Okay, so putting this capacitor somewhere, basically between power and ground. I like to keep it close if I can. So we got our, ground anywhere really. Power comes in here. So it might be good to just put it, put it kind of close to these op amps here. So it's kind of skinny just because it's going to have to be thermal relief anyway. We'll just double up on this ground connection here. Yeah, you know what? Might as well make this one 16 if we made the other one 16. Okay, so now we got our decoupling cap here, and then we hit. How's everything looking? That looks good. Now, if we don't want to use that diode, right? So if we end up saying, no, my design doesn't need it, I've got the diode there, I don't need it. One thing is these diodes are commonly, these pads are really close together. So it's very easy to short these, not with solder, but you can just put like a 0 ohm resistor across there. There's another thing we can do. which is we can do a cut trace. So we can do a cut trace, which is basically a part that says, I'm going to default to being connected. And if you want to use this, if you want to disconnect this, so in this case, if you want to use this diode, if you want to have a diode here because you're noticing you're having an issue, you have to cut the trace, and then it'll sort of have this connection. So basically, it's going to short these pads as by default. Only when you cut the trace is it going to use it. So I'll show you how you can do that. That's components. I think we have them in the EE library. We don't. Huh. Could have swore we had a cut trace. Well, they're easy enough to make if we don't have one. But if I can't find that, I wouldn't put it there. I mean, an easy way to make one is to basically, oops, always want to look for that red. I want to look for that red connection to show you're actually connecting. So all I've done is shorted. I put a wire here, and if I update the PCB document, so now it's saying that these two pads need to be shorted. And what I can just do is I can just make this, pretty thin. It's kind of short. It doesn't need to be too thick. So it's a little wire. So if I come in here with a razor blade and I cut it, so it's shorted, we don't have to populate this diode. If we want to use this diode, we can come in here and cut it. If we want to make it even easier for ourselves, I'll show you something else you can do. If we want to make it easier for ourselves, we can go to, so if we look at this right now, in 3D view, this is what it looks like, right? So we would have to cut through this top solder mask to get to that thing. But if we want, we can also do this. We can go to the top solder layer. So top solder layer, which normally you don't see, and then we can place a solid region. Okay, so now look at that. Right now we made a little window. We have a little window in here that exposes that trace there. And there's other cool stuff you can do when you're playing with the solder. So some students like to get really creative. They like to spend time on their board design. So another kind of cool thing you can do if we got time. We don't really have time because I'm about to. You'll notice the time. I'm about to start heading up there for lab. But if we, oops, I'm going to show you something kind of nifty here. Flipboard. Okay, so I got to turn my, I do want to see this. Okay. Um, so what if I take my Viking here? And it was sort of bottom solder layer. And I select the whole thing. And set my grid kind of coarse here. And I say, oops. Actually, the first thing I'm going to do, I'm going to copy this. Select. Oops. So I'm going to paste a copy of it over itself. So I have two of these now. So I copy pasted this. So I have two. I must select one of them. Oops, apparently I'm not. Apparently I could get away with that. Just happened. Okay, so I got two of them. So one of them I'm going to make to bottom copper, bottom layer. Okay, and the other one I'm going to make into solder. Actually, this might be an issue because you might have to do 6 mil at least on this copper to do this. And you probably want to align it better than me. What I just did now, shoot. So we now do this. Oh yeah, it's gonna hit that thing. Ah, shoot. Well, we'd have to put it somewhere where there's no, we have to put it somewhere where there's no conflicting metal. But if we did, I just want to show you what it looks like. If we did that, it's exposed metal, right? So if we do a metal layer and then a solder mask layer that's the exact same thing, where now our logo is going to be made out of metal, which is kind of cool. But I think when you do this, when you import the image, you have to set the thickness to 6 mil. So this is a neat little game that some students play. And I'm going to Control Z this thing. Go back to normal. Okay. All right, that's all. That's all I want to show you.